All right, hello everybody. Just figured out, I guess this is day 5 of our slog through metabolism. So you're doing well. We're going to finish the citric acid cycle today, and then we're going to get back to some really interesting reactions, and I'm excited to talk about them because I'm learning this stuff too. I've got a bunch of notes here from Dr. Michaelis, who's a world expert at organometallic chemistry. We're going to learn some interesting things about transition metals. But in the meantime, let's review where we were last time for the citric acid cycle. We've got acetyl-CoA, which, as you remember, we can get either from glycolysis in the pyruvate dehydrogenase complex, or we can get that from fatty acid beta oxidation, both of which we've learned about, or we can get it from amino acid metabolism, which we haven't talked about. So citric acid cycle entry point begins with oxaloacetate and acetyl-CoA, and the reaction is basically aldol. You make an enolate, then that negatively charged alpha carbon attacks the carbonyl carbon of the ketone. We get a tetrahedral intermediate, and that negatively charged oxygen gets protonated. And then we get this thioester product, and here is the new bond that we made. These two carbons come from acetyl-CoA. Then we hydrolyze the thioester with a nucleophilic acyl substitution reaction, and we didn't draw the mechanism of that because it's something that you should be familiar with. And then once the resulting acid loses its proton due to its pKa at physiological pH, we end up with citrate. And notice that citrate is not chiral. And so right away, we've lost track. I mean, we could continue to say these two carbons came from acetyl-CoA, but we could just as easily say those two carbons came from acetyl-CoA. We just don't know. All right. So our goal in this process, as I think I mentioned yesterday, we've got a couple of goals. One is to lose 2 CO2 molecules. And then second is, after we've done that, regenerate the oxaloacetate starting material. And so our methods that we know for losing a CO2 molecule is decarboxylation of a beta keto acid, which we saw before in the malonic and acetoacetic ester synthesis. Or alternatively, we can do oxidative decarboxylation of an alpha keto acid, and that's what we did last time with the pyruvate dehydrogenase complex, and that required thiamine, pyrophosphate ylide, and lipoate as cofactors. So we got 2 different methods for decarboxylating. So let's get a sense for where we are. Here is citrate, and as an aldol product, citrate is, if this is a carbonyl carbon alpha beta, citrate is a beta hydroxy alcohol, and I suppose it's also beta to the other carbonyl, though I guess it would be alpha to the blue carbonyl. Now, as you look at our methods, we want either a beta keto acid or an alpha keto acid. And the problem is that citrate has a tertiary alcohol. And can you oxidize a tertiary alcohol? Nuh-uh. The reason is that the oxidation reaction mechanism in biology for alcohols involves a base removing this proton, and then a hydride with its electrons gets delivered to NAD+, right? So if you don't have a hydride, you can't oxidize. There's no hydride there, so we can't make this tertiary alcoholic ketone, therefore we can't get to an alpha keto acid or a beta keto acid. But not to worry, we've got a couple of simple steps that are going to get us there. So the next reaction is to take, and sometimes I think people show these reactions together. So sometimes they may skip. I'm going to show you an intermediate that has a name. They may skip that and just use, just go directly from citrate to the final product. What we're going to do is E1CB style dehydration. This is something that happens in the aldol reaction. Sometimes after we make the new carbon-carbon bond, we can have a base remove an alpha proton to make an enolate. And then the resulting enolate, negatively charged electrons on the alpha carbon, can kick down and remove the OH group on the beta carbon. So for right now, I'm just going to stick with carbonyl carbon alpha and beta carbons. Okay, so this is the dehydration reaction, and it's going to give us as a product the following molecule. Okay, so this molecule is called cis-aconitate. And similarities to things you've seen before. This is just an alpha-beta unsaturated carbonyl compound. Though we will point out that it is alpha-beta unsaturated in a couple of directions. That is, relative to the yellow carbonyl, here's the alpha carbon, there's the beta carbon, but relative to the blue carbonyl, here's the alpha carbon and there's the beta carbon. Okay, do you see those two options? It's a ene diacid, basically. Okay, so remember that our key problem was the oxygen was on a tertiary carbon. Is there a reaction I could do to now, on this alpha-beta unsaturated carbonyl compound, to get the OH on a secondary carbon? A reaction that you know or have seen before. Brief refresher, alpha-beta unsaturated carbonyl compounds are electrophilic at the carbonyl carbon, but also at the beta carbon. So a nucleophile can attack the beta carbon. All right, well, let's suppose OH minus is our nucleophile. If OH minus were to attack the yellow beta carbon, that would just take us back to this previous step. Right? Do you see how if OH minus attacked there, and then we would move these electrons here, and that would get us to this enolate. And that happens all the time. But what if OH minus attacks the blue beta carbon? Let's show what happens there. So attacking the blue beta carbon, electrons would need to move up onto the blue alpha carbon as an enolate. Sorry. And that would give us this intermediate, with an OH group on that carbon. Do you see how we got there? It's just conjugate addition of a nucleophile to the beta carbon of an alpha-beta unsaturated carbonyl compound. And then this can pick up a proton from some source, either an enzyme side chain or perhaps water. And the product that we get at that point is an isomer of citrate, where the only difference is the OH group is located in a different spot. So this molecule is called isocitrate. And as you can see, it differs only from citrate only in the location of that OH group. All right. Questions about those steps? Isocitrate is chiral. Notice that in this reaction we made two stereocenters, one here and one there. Stereochemistry there is known. I'm just not drawing it for you now. And frankly, we got bigger fish to fry than for me to try to deceive you with non-physiologically relevant diastereomers of isocitrate. So I don't particularly care that you know the stereocenters there. The enzyme that catalyzes this reaction is called aconitase, because of this intermediate aconitate, which can either go back to citrate or on to isocitrate. The reaction is reversible. It's an equilibrium reaction. You can go backwards and forwards depending on relative concentrations of stuff. If you want to actually see the stereochemistry, it's up there and it's up there. But as I said, I don't particularly care that you know that stereochemistry would of course be controlled by the enzyme. And I kind of don't like the way I drew all of that. Okay. All right, so now this is progress because we're in a situation now where we've got an OH group that can be oxidized. And notice that this OH group is beta to one carbonyl and alpha to another. So we've got that in the perfect spot to lose this CO2 group and to lose that one if we oxidize this OH to a ketone. All right. Remembering that one of our goals is to get rid of a couple of CO2 molecules, we said we can do that from an alpha keto acid or from a beta keto acid. We've now got this OH and it's on a secondary carbon, so it's oxidizable. If we oxidize that to the ketone, we would then be prepared for two different decarboxylations, one of this CO2 and then the other decarboxylation of that one. Okay, so let's take isocitrate to the next step. And this is where we're going to oxidize isocitrate to the corresponding ketone. So we'll call this, I don't know, steps 4 and 5. Again, because sometimes people don't draw out the intermediate because the resulting decarboxylation reaction is just so fast. I will draw out the intermediate and we'll name it, but just understand that some folks won't. Whether or not you consider it a separate step of the citric acid cycle doesn't really matter. All right, so we're going to begin with isocitrate. we're going to use NAD+. And because you've seen NAD-based oxidations before, I'm not going to draw this mechanism out in full. What will happen is that a base will remove this proton. Electrons will kick down to form the new carbonyl. This hydride will leave with its electrons and be delivered straight to NAD+. And that's going to give you the following intermediate. Sorry, 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so we've oxidized that hydroxy group to a ketone. The other thing we will have, of course, is NADH. Again, I'm not going to draw, you've seen NADH arrows drawn a lot of times. You've seen the structure of NAD plus versus NADH. So this is just the typical NAD plus based oxidation reaction. The enzyme that catalyzes this is called isocitrate dehydrogenase, because we're removing a proton and a hydride from the molecule when it gets oxidized. Notice that our product is both an alpha keto acid and a beta keto acid. And this intermediate is called oxalosuccinate. And this is the one that some people don't consider as a step along the citric acid cycle because it's short-lived. In fact, what happens as soon as we make the the beta keto acid, we get this decarboxylation step. Electrons kick down to make CO2, and then the electrons in this bond go to the alpha carbon where they are stabilized by resonance. All right, loss of CO2 is irreversible. And having lost one CO2, we're left with a 5-carbon molecule. And this is the enolate. And we're going to show, some people will show this enolate getting protonated on the oxygen first and then tautomerizing back from the enol to the ketone. I think we're just going to not do that. We'll just save ourselves some time. And just protonate that enolate on the alpha carbon to get our product, which is this following 5-carbon alpha keto acid, which is called Alphaketoglutarate. It's 5 carbons long. So here's one of the CO2s. We can check that off our list. And after step 5, we're set up with an alpha keto acid to do another decarboxylation, only this time it's going to be oxidative, like we did in the pyruvate dehydrogenase complex. Okay, questions so far? One interesting thing about alpha-ketoglutarate, I mean, we'll show what happens next, but nature can use alpha-ketoglutarate for a bunch of other things. For example, if you used pyridoxylamine. You'll have to go way back in your notes to the imine chapter when we talked about what pyridoxylamine is, and a transaminase enzyme. You can actually swap out the ketone for an amino group. And if you do that, lo and behold, what amino acid do you have? Ha ha ha, you jettisoned all that information after exam 3. I'm going to get you. Some of you are saying glutamate. You can tell the difference between glutamate and aspartate because in glutamate, the carboxyl group is on the delta carbon, whereas in aspartate, it's on the gamma carbon. Okay, so nature will, sometimes, one of the ways you can make glutamate, if you need it, is to siphon off alpha-ketoglutarate as that source. By the way, if you want to, you can go back and look at oxaloacetate and imagine doing the same reaction, installing an amino group there. Then what would you have? Aspartate, right? Okay, so that's not anything that will, I mean, if I showed you that mechanism, you've seen it before, you should go back and look at your notes and notice how imine formation and some tautomerization allows this process to occur. That's sort of a side note. And as you take biochemistry, you may learn about that reaction, and so that's another use for alpha-ketoglutarate. But that's not, I'm going to put this in parentheses because that's not what happens in the citric acid cycle. That's amino acid synthesis. Okay, so next we will take alpha-ketoglutarate. And we'll call this step 6, I think, yeah. Alpha-ketoglutarate. And we're going to use as cofactors TPP, lipoate, ultimately, I think both FAD and NAD plus. And actually, we can just say NAD plus, and I think that's probably good enough. And then let's see, thiamine pyrophosphate ylide. Oh, I've already written that. Lipoate, and the enzyme that does this is called the alpha-ketoglutarate dehydrogenase complex. And I'll refer you to the conversion of pyruvate to acetyl-CoA to see how this happens. It involves decarboxylation, removal of this carboxylate group as CO2, and then what's left behind is a thioester, just as we did before in the conversion of pyruvate to acetyl-CoA. All right, so I'm sorry, I guess I should put coenzyme A as a reagent because it's not like a catalyst, it's consumed in the reaction. So let's put coenzyme A here. Let's also put NAD plus here, and we'll get NADH out. All right? So you can go back and see that mechanism, but basically I'll get you going on a first couple of steps. Remember that TPP ylide looks like this. It's a nucleophile where the nucleophile attacks the carbonyl carbon of the ketone, and you get an intermediate that looks like this. Sorry, we'll show that ketone first getting protonated I'll draw the intermediate and then just sort of remind you of what happens next. Oh, goodness, that's not right. All right, remember that we're now set up for decarboxylation because the beta carbon here is kind of like a carbonyl, and if we did the decarboxylation reaction, the resulting anion would be resonance stabilized. So that's the first step of many. You're going to decarboxylate, and then you're going to oxidize this alpha carbon up to the carboxylic acid level, and you're going to make the thioester. And all of this will happen mechanistically exactly like the pyruvate dehydrogenase complex that converts pyruvate into acetyl-CoA. All right? Anything you want to ask about that step? Anything you're still confused about from pyruvate to acetyl-CoA? All right. This molecule here is called succinyl-CoA. And succinic acid is a diacid that's 4 carbons long. This is a thioester. And now we've lost our second equivalent of CO2. So goal 1 has been accomplished. Now, if you look at this molecule relative to oxalosuccinate or oxaloacetate. In oxaloacetate, you're going to have a ketone on this alpha carbon, and you'll have just a carboxylic acid here. So we've got a few steps. We need to somehow oxidize this CH2 group up to the level of a ketone, and then we need to hydrolyze this thioester to a carboxylic acid. The interesting thing, though, is that thioesters are relatively high energy compounds. They're because the thiol is a good leaving group. And so nature doesn't actually want to just hydrolyze that thioester. We're actually going to use it to make GTP, which can sort of be used interchangeably with ATP. So we'll begin with acetyl-CoA, and here's our 4-carbon acid. And we're going to take phosphate and have that add as a nucleophile, doing a nucleophilic acyl substitution. Where you're going to get a tetrahedral intermediate, negatively charged oxygen, once that phosphate group gets attached, the pKa of the other OH group drops low enough that the proton falls off. So I'm just going to show that happening directly. 1, 2, 3, 4. Okay, and then electrons will kick down and leaving group will leave. And the product from that step is a mixed anhydride. That is, you've got a carboxylate group attached to a phosphate group. Sometimes this is called an acyl phosphate, which is fine, but I like to call it a mixed anhydride. And remember, back in glycolysis, we use this for substrate level phosphorylation because all of this is a good leaving group. Yeah. All right. So now we're ready to have GDP, and I'm not sure how best to draw this. Maybe we'll just call it GDP. We'll have R here, and here's the beta phosphate group of GDP. This reaction is going to be basically SN2 style. Negatively charged oxygen attacks phosphorus to make a new bond, and we break that bond. After that's done, we get GTP as a product, which we can use interchangeably with ATP. And then we've got our 4-carbon acid, which is just called succinate. All right. Questions? So that shouldn't look like a terribly new reaction. You're used to thioester hydrolysis, this sort of nucleophilic acyl substitution reaction, and then, except I can't spell substitution, and then you have this basically SN2 style substrate level phosphorylation where we break the mixed anhydride and transfer the phosphates to GTP. Okay, so we're only, let's see, is it 2 or 3 steps from the end? I'm tired yet? It's actually 3, but they're easy. Sure. Sure, how about that? Okay. Have faith. Sorry, I'm looking at stuff. I've got some interesting but irrelevant stuff in my notes, so I'm trying to filter out the irrelevant stuff. Okay, so starting with succinate, we now want to oxidize the alpha carbon of succinate, one of the 2 equivalent alpha carbons, to get a ketone there, right? So the first step is going to be similar to something we saw in fatty acid synthesis. And we're going to use FAD. And at the end of the reaction, we're going to have this molecule where we've installed a double bond between alpha and beta carbons. And we'll get FADH2, which can then go to the electron transport chain. So the way this happens is it's an E1CB style mechanism. We're going to remove a proton, remove an alpha proton to get an enolate. Oops. And then that enolate is going to, electrons will kick down to make a new pi bond, and then hydride will leave with its electrons and be delivered to FAD. Probably, since FAD is a little bit more complicated than NADH, I'll go ahead and draw this part of the mechanism again. So hydride gets delivered to this nitrogen of FAD, and then we pick up a proton from another source. And that will get us to the products FADH2. And let's see. The enzyme that does this is called succinate dehydrogenase, because this is an oxidation reaction. And where is that hydrogen? Well, in FADH2, you've got the hydride that's here and the proton that's there. The product is called fumarate. And I'm not sure why, but every time I see that, my brain focuses in on the infinitive of the Spanish verb to smoke. So I don't know. Which I had to learn on my mission because, of course, we talk about how we no fumamos. Okay. Questions? So if you go back and look at your fatty acid beta oxidation, this is exactly the same mechanism of the oxidation step. Let's see. No, that's right. That's exactly the same mechanism as as one of the steps in fatty acid beta oxidation. And actually, the remaining two steps are going to follow along analogously. So you got fumarate, or there's some weird Christmas song called Foom, Foom, Foom. So I don't know. And we're going to add water, or OH minus is fine. And we're going to do, again, conjugate addition of a nucleophile to the beta carbon of an alpha beta unsaturated carbonyl compound. Notice that both of those carbons are at the same time alpha and beta, so it doesn't matter which one. We'll go ahead and show, and the mechanism, I guess, is conjugate addition. We'll go ahead and show the lone pair on the hydroxide attacking here, and then electrons will move on to that alpha carbon to give you an enolate. And we make a stereocenter, and the stereochemistry of that stereocenter is this. I don't care that you know that. 2, 3, 4. We'd have a negative charge on that carbon, and then we'd pick up a proton to give us the final, or the product L-malate. Now we've got an OH group on the carbon adjacent to the carboxylic acid. That's good because we ultimately want to regenerate oxaloacetate. And now we can do that just by a simple reaction, a simple oxidation reaction. The enzyme that catalyzes this one is called fumarase. And then finally, our last step, did we do 2 steps 9? No, I guess we're fine. Our last step is just an NADH or NAD plus oxidation of malate. And I won't show you this mechanism because it's exactly the same as you've seen for other NAD plus based oxidations. That will take us back to oxaloacetate, and we've turned the crank once. And let's see, this enzyme is called malate dehydrogenase. Okay, so one turn, we've lost CO2, 2 molecules of CO2, we've regenerated oxaloacetate, and along the way, we've made some molecules that we can use in other areas in biology. So let's try to keep track, okay? We have, and maybe we'll use celebratory firework explosion indicators for energy-rich molecules. So we've got, that's one NADH. Okay, there's another FADH2. Okay. What else? We've got another GTP, which we can use equivalently with ATP, though there are some unique uses for GTP in the cell, signal transduction and so on. Continuing back, let's see, when we oxidized isocitrate to oxalosuccinate, there's another NADH. Dun, dun, dun. And then I think that's it, right? Step 6, did I miss one? Ah, surprise. Another one. They're hiding all over the place. Okay, so if we zoom out, I'm counting 1, 2, 3 molecules of NADH, 1 of FADH2, and 1 GTP. Is that right? So, 1 turn of the citric acid cycle, starting with 1 acetyl-CoA, gives us 3 NADH, 1 FADH2, and 1 GTP. And of course, there are 2 per glucose. So that would be 6, 2, and 2. And then each NADH can make 2.5 to 3 ATP. I think your text says 2.5 in the electron transport chain. So we'll go with that. What is that, 15? 15 ATP from there. 1.5 from FADH2 in the electron transport chain. That's 3. And then sort of 2 ATP equivalents. So overall, doing some math that I'm not good at, 20 ATP molecules from taking the 2 acetyl-CoAs from the citric acid cycle and taking these molecules to the electron transport chain. So that's quite a bit more than we got from glycolysis, and this is why aerobic respiration is so important. You can survive for a while on anaerobic respiration, but not too long. Okay. What else do you want to talk about there? Yeah?
For step 7, was there a enzyme?
Yes, there was, but I forgot to talk about it. And let's see if we can guess what it's named. We start out with succinyl-CoA, and we end up with succinate. My guess is the enzyme is succinate kinase, because if you went backwards, that would be putting a phosphate group on succinate. So let's see. It's not really a guess for me because I have the notes in front of me. Sorry, I'm mixed up on who's what. Oh, wrong. Okay, well, that's fine. This is called succinyl-CoA synthetase. And that's named for the backwards reaction. The backwards reaction would be you phosphorylate this oxygen to get the acyl phosphate, and then CoA attacks to create this molecule. It's a synthase because we make a succinyl-CoA. It's a synthetase because we consume GTP in the process. So it is named for the backwards reaction. Get my own question wrong. It's okay. Did I miss any others? I think that's pretty much it. What else? All right, let's close the book on metabolism. We're done with that. And now let's talk about chemistry. And let's think about all of the carbon-carbon bond-forming reactions we have learned so far. For example, one of the first you learned from 351 was that you could take this alkyne and then some alkyl halide and make a new carbon-carbon bond between the sp hybridized carbon of the alkyne and the sp3 carbon of the alkyl halide. So, and sometimes when we make carbon-carbon bond forming, when we make carbon-carbon bonds, it's useful to classify these reactions according to the type of carbon-carbon bond they make. So this is a bond between an sp carbon and an sp3 carbon. We've learned others. So early on in this semester, we did organolithium/Grignard reactions. We'll just give you one of those examples, but that makes a new carbon-carbon bond, converts, and usually the organolithium is some kind of alkyl group, usually a primary alkyl group. So in the Grignard and organolithium reactions, we make a bond between sp3 hybridized sp3 hybridized carbons. And then, of course, we'll do the similar thing if we start with an ester and use the same conditions, only we will get the tertiary alcohols. So we can make two new carbon-carbon bonds at the same, oops, that's a Texas carbon, at the same time, provided we start with an ester. Starting to look vaguely familiar-ish. Remember that if you started with an acid chloride and used a cuprate, that you can make a bond between the carbonyl and an sp3 hybridized carbon from the cuprate. So that's a sp2 to sp3 bond where this one's involved in a carbonyl. So at that stage, our abilities were growing. We learned other things you can do with cuprates. For example, the alpha-beta unsaturated carbonyl compound, we learned that the cuprate would add to the beta carbon, and that had to do something with the nucleophilicity of the cuprate reagent and its different properties relative to like an organolithium reagent. But that would make a new carbon-carbon bond here. And let's, in each of these cases, highlight the new carbon-carbon bonds that are formed. Okay, so this is a sp3 to sp3 type carbon-carbon bond. And that was a lot, but then we made it worse. Right? We did enolate alkylation, where you could take some ketone and then you could use LDA to quantitatively make the less substituted enolate, and then you could add an alkyl halide, and that would allow you to make a new bond here. And that's also an sp3 carbon-hydrogen bond. And then I guess the last two would just be aldol/Claisen, where you make that new carbon-carbon bond, or the Michael reaction, where you make this new carbon-carbon bond. You didn't think we could summarize most of 352 in like 3 minutes, but that was it. Okay? That's all of the carbon-carbon bond forming reactions that we've talked about. And notice that with very few exceptions, they're all about sp3 hybridized carbons. We've got one exception here with an sp hybridized carbon, And we've got one exception here with the cuprate where we make a ketone. Other than that, you got sp3 hybridized carbons bonding to each other, which is great. But as synthetic chemists, we want more tools because there's a lot of molecules that have interesting properties with carbon-carbon bonds involving sp2 to sp3 or sp2 to sp2 kind of bonds. So stay tuned for the continuing story of carbon-carbon bond formation, which we will continue with on Monday.